With a mixed up audience actually.
Yeah, mixed up audience. So let's start. So we welcome you, sir, in this lecture. We are very thankful to you that you have given your precious time and giving some evaluation in this lecture. Although we are expecting that you will be here in offline mode, but unfortunately that didn't. You were not able to make it up for that. But we hope that we'll see you soon here in offline mode also.
Yeah, sure. I will.
Thank you. So, dear students and participants, we have with us Dr. Amit Shukla. He is the chairperson, Center for Artificial Intelligence and Robotics, IIT Mandi. His area of specializations include robotic control systems, mechatronics, AI, electric vehicles. Dr. Amit is having PhD from Imperial College London, UK, BTech and MTech from IIT Kanpur. He is also a successful entrepreneur. He has founded around 3 startups. So we welcome you, sir, in this lecture. And today, Dr. Amit will deliver a lecture about introduction to robotics and robotic kinematics and dynamics. It's over to you, sir. Please start.
Okay. So thank you very much. Very good afternoon, all the students and participants. Since it's a very, like audience, like people have a background, do not mind if you not understand, few things because you may require some background of linear algebra and mathematics actually. So, frankly speaking, robotics is nothing but mathematics. Obviously, you have a physical applications of out of it actually. So what I will do, unfortunately I couldn't be among you because I was attending Indian Space Conference actually, so I was in Delhi. And because of this lot of travel, the conference is still going on. I thought, okay, it will take some time to deliver the lecture. And okay, so what I will do, since I have only 1 hour, and the topic it is quite deep actually, because robot kinematics, because when you go for a robotic, the first thing is this, will you please share my screen? My screen becomes really big, don't let me know. So, my screen is visible now actually.
Yes, sir.
Okay, so someone told me it is a kind of a drone boot camp or something like this, so I just put a title here. So, what I will be doing that, because I'll give a very elaborate introduction to robotics actually, where I go into the history, contemporary time actually, and we go into the future. Then I teach a full semester course on robot kinematics, dynamics, and control, which involve at least 5-6 lecture on the introduction to robotics itself. But unfortunately, due to time constraint, I am not able to go fully here into the introduction part. So I'll be starting from the foundation of robotics, that is called kinematics actually. So kinematics part I will try to cover. So if you see here, in the robotics, one of the most important things, like when you define any robotic system, is this: what is a robot and where it is in the space actually. So generally, if you see the traditional definition, a robot is a mechanically constructed by connecting set of bodies, which is called links actually. So keep in mind that it's a rigid body, and this rigid body, they are connected through some joints, and then we construct the body. So frankly speaking, the robotics in the current time is nothing but an embodied AI actually. So the development of robotics and AI goes hand to hand in parallel actually. As AI is developing, we are getting more advanced robotic systems actually. So robotic systems are having one of the most important things is this, like embodied AI in the sense intelligence on board a physical system. A physical system which can move, interact in the environment, which can navigate in the environment, which can manipulate the environment, can sense the environment. So that's the reason if I give a correct name to the robotics, I will call it embodied AI. So robotics has the 4 pillars. one of the first pillar of robotics is the body itself actually, or the chassis, on which all the sensors are installed, on the computer is installed, which will collecting the environment, which will moving in the environment, which will manipulating the environment. So robot body itself. This is where we require a good knowledge of physics, mechanics, or you can say some part of mechanical engineering actually, where this chassis can be built. The second component of robotics or any robot is about actuators actually, or you can because the reason is because the robot has to move in the environment, has to navigate in the environment, interact with the environment, or manipulate the environment. And actuators are
इधर भी कैमरा में आगे
control theory. So, the part is the whole robotics itself, or robot body itself, actually, how do you do that? The second part is this actuators. Because the actuators are supervised. I didn't mention you are the mechanical functions, and these are actuated by electric joints. And most of them is actually are motors actually, that you can have a pneumatic, you can have different other kind of actuation is also possible. But most of the time in common era in current situation, they use electrical it has a very super performance actually. This is a talk in the last week. Very good actually. So that's the reason you can also get lightweight actuators actually. So lightweight actually means there is a very large part and force and pay to its weight. But if you look to the pneumatic and other system, they will be quite heavy actually. Compare what kind of force and torque they can apply actually. And also the control balance is not as fast, or the firing balance is not as control systems, and this control systems is used to manipulate the actuators so that we can get a desired performance or desired actuation. Environment, or it is a terrain environment actually, or terrestrial environment, or it can be hybrid or combination. So what is that? So persistent environment is the third most important thing. And once you perceive the environment, the process of perception requires a lot of AI actually. Earlier we used to have a classical computer vision, and now we have deep learning based or AI based computer vision actually. Not only the computer vision, we have other way of perception environment like GPS, that can be LiDARs, that can be magnetic sensor, acoustic, thermals. There are n number of data assets on how you perceive and model the environment actually. And a lot of algorithms like some algorithms look like mapping, SLAM, and all those region SLAMs are there. There are so many technologies are there in this third area, and a lot of AI sits here actually, because when you perceive the environment, you have to understand it actually. It's like that is one of the area in computer science or computer vision or robot is called scene understanding actually. So when you understand the scene, you understand what this looks like, where is the obstacles, where is the open path, where is the passage, what is my target, what is my the current location. So all these things comes think into the area of computer vision, in the area of scene understanding, scene perception. So the perception model, which is mostly in current times made of AI, is the third pillar of robotics. And the fourth pillar of robotics, for this scene understanding, for this actuation and all those, you do require sensor. The sensor which can tell you what is the current situation, what is the current data which is coming from the environment actually. Current, I'm not talking about the voltage of current, I'm talking about the real time actually. So, because most of the time we are expecting the robot to deal with the realistic environment, very much like a human being navigating or manipulating or interacting with the real environment with similar situation. So this is very important, and as I mentioned that there are different kind of sensors out there. You can have a visual sensor, audio sensor, touch sensor. You can have electromagnetic, magnetic. You can have acoustic. You can have a thermal. You can have a laser. There are n number. Means you can just name it actually. There are so many sensors out there actually. So humidity sensor, pressure sensor, temperature sensor. So the sensor understanding makes the fourth pillar of robotics actually. So as as you can understand now that robotics is highly interdisciplinary, and that's the reason generally it is not taught into the undergraduate programs, because it does require you to have a lot of background actually to make a robot, and this actual robot. You have to have a lot of understanding of robotic system, then also the control system, then you have to have a good understanding and command of the AI, and then the fourth, you have to have a very good understanding of the sensors actually. When all these four pillars, when they come together, then you are able to make a functioning robot. And one of the example I will quote, if you see that autonomous driving cars, and if you see that space example, like currently I'm attending one of the Indian space conclave actually, and in this space you cannot do anything without robotics actually, or AI. The reason is because controlling a Mars rover mission or Chandrayaan mission from the ground, without having a very high level of autonomy is next to impossible, because bi-directional data travel itself will take half an hour actually. So by the time point to point or teleoperated control is just next to impossible. So you have to have a very high degree of autonomy, and that high degree of autonomy is only possible when we understand all these four principles which I mentioned actually. So now let's come to the so in this today's lecture I will be talking about the first part actually. The rest of the part definitely I'm sure you must be learning in your courses actually, and when you interact with the expert member and do some project hands-on actually, you will have a learning. But as I mentioned that a lot of foundation is made of mathematics that we will talk about today actually, but do not worry, mostly I'll be talking about algebra. So so idea here is this, once you have this mechanically connected links, and these links are connected to the joints, and the joints you have this actuators actually, and these actuators they generate the torque related to each link actually, and then this makes the robot to move actually. So generally what happens, you also have, if you go to the example of one of the common robot which we see is a serial manipulator, you also have something called the end link, also called as the end effect. Move it and interact with the scene environment actually. So that is called end effector. So why I'm telling this terminology, because when you do robotics, you'll be hearing this a lot. Links, joint, actuator, end effector. So you should be knowing what this stands for actually. And so this end effector are mostly grippers actually. Generally you will find a 2-finger gripper, which is very common and also very easy to control. The only thing is you know to perform all the tasks needed actually. So there are 3-finger grippers, and there are also like a full-fledged, like a human, like a hand, like a grasping mechanism is also there actually, and that is attached to the end of the link. One of the most fundamental questions in robot, once you build the robot, like for example, it can be autonomous ground vehicle, it can be alien vehicle, it can be manipulator, it can be anything actually. So one of the most fundamental questions once you build the robot in the scene is this: where this robot is actually. And this question, like for example, when you are studying in the class, when in the university, you want to go to your classroom or your canteen or anywhere, so you first like to know where I am and where I want to go actually, where is my desired, or destination basically. So this question in robotics is considered something called configuration actually. So when I know the configuration of the robot, I know the complete specification of the positions of the robot actually. So if I read the exact definition, it says that specification of the positions of all points of the robot, this defines the configuration. And someone may ask me this question, like a robot may be made of unlimited number of points actually, or maybe very, very large actually. So how do I know its definition of each point of the robot actually? So that is where the earlier definition comes to help you, which we are talking about links. And these are the rigid links, rigid bodies. So since the robot links are rigid and they are of a known shape, once you fabricate them, and once you have designed them, you have chosen them, you put in the place actually, you know what shape, you know, and they have a rigidity actually. So only few number of parameters are required to define the configuration of the robot actually. So once you know the configuration of the robot, then your journey starts. So how do we know the configuration of the robot? We will come to know in the coming slide about the definition of it actually. And let me give you some quick visual overview actually. So suppose that, am I clear to everyone?
Yes, sir.
How many audio?
Am I audible? Because I'm not getting any feedback, so sometimes what I do, I remember I did a lot of classes during Corona and many times I used to come teaching for how and how my class is disconnected. So if anyone had a question, please you can ask me, you can stop me somewhere, but it just started actually. Nonetheless, if you have any question, you can always ask me. So suppose that if I have this is the first example I can show you. This is the like a manipulator here actually, single manipulator because the loops are singly connected here, and you can see that to define each point of this robot, the configuration of the robot, you just define only two parameters. What is those parameter? Because these robot links are made of rigid bodies actually, and you can see that actuators here is a rotation. The first link is rotated, the second link is also rotation, the third link is about like a prismatic joint or translational joint actually. So only these three parameters will be more sufficient to define each point of the robot actually. So you will, if you have a parameter Q1 is known to you, if you know the Q2 and if you know the Q3. So these are the parameters, obviously the link length L1, L2 and L3, they are fixed actually. So if you know these parameters, you will be able to define each position, like each position of each point of the robot, and that is called your configuration actually. Similarly, if you go to the, you can see the physical example, like if you, I'm sure you are undergraduate and the mechanics problem you must have done when you solve a problem, you always go for a full body diagram. So similarly, your robot may be of a complex shape, but when you draw a body diagram, a full body diagram, you try to put all these parameters and try to get an abstract model actually, which is wrote in the form of a mathematical equations. So once you draw a free body diagram, you write these parameters sections and define the configuration of the robot, and when you write the mathematical equations, then you can forget about the body actually, because now those equations will govern the motion of the system actually. So similarly, if you see here this Pucha robot, which is a manipulator actually, and this manipulator is installed on the ground level actually. So let me see if I can get the laser pointer. Okay. Yes, so here you can see that it has a 4 wheels actually, and this is obligational wheels, and then you have a wheels like a manipulator which is attached to it. Now this robot configuration space will be the parameter which are defining the rotation of these 4 wheels, and also the parameter which are defining the rotation of this joint actually. So now you can see that this is a very high degree freedom system actually, and if you combine them, the degree of freedom more than like a number of degree freedom in the system can be very, very high. Similarly, you can have a drone which have which is a hexacopter with 2 manipulators installed in, which are having a 2 degree freedom actually. So you can see here the configuration space will be governed by the rotation of these propellers and also the rotation of the joint space of this manipulator actually. So this is called configuration space. Please try to understand this configuration space is not a physical space where we try to see where my robot is actually. This configuration space is an abstract mathematical space where each point in the configuration space tells me where is is the robot, what is the configuration of the robot actually, what is the orientation, what manipulator is doing, what is the wheels are doing, what each component are doing actually. So this is a mathematical space, this is abstract space, this is not a physical space, because we can have a configuration space of 100 degrees, we can have a configuration space of a 200 degree actually. Like for example, there are many snake robots are there are many highly redundant manipulators are there. So configuration space is not should not be thought as a physical space, because your physical space cannot have more than 6 dimensions actually. But your configuration space can be very high dimensional, depending on kind of links you have actually, kind of joints you have actually, and what is the configuration, how the robot is connected, how the links are connected, you can have a very high level freedom. But each point in a configuration space, like for example, if I go in that dimension. Okay, every point in that dimension will give you unique configuration of the robot actually. So that is the definition of the configuration space, and it is very useful. Why we should know the configuration space? I will come to the coming slide to explain that why we require to know the configuration space. So configuration space is specification of the position of all points of a mechanism. Configuration of a robot is a complete specification of the position of every point of the robot. And then, what is the dimension of the configuration space? Configuration space, the dimension of configuration space goes to the degree of freedom of that robot. And the minimum, and what is the degree of freedom? How do we define? The degree of freedom is number of parameters, and they should be real value. Number of parameters to define that configuration. So minimum number of real value coordinates required to represent the configuration is called the degree of freedom of the robot actually. So for example, in this case, you require 3 parameters, Q1, Q2, and Q3. So your degree of freedom is also 3, and dimension of configuration space is also 3. So configuration space is n-dimensional space containing all possible configuration of robot is called configuration space, or in a short, we will be hearing or reading the like a research paper or the robotics book, they will call it as a C space actually. So this C space, it is define the like a degree of freedom actually the robot which is containing that. Let me go and let's do some, how do we calculate, this degree of freedom of any mechanism actually. Some of you who are coming from a school of mechanical engineering, maybe knowing if you have done, electricity with your senior students, those are the theory of machines actually. They must have gone through this actually. So I think in this, the degree of freedom of the mechanism means the summation of total degree of freedom of the body minus independent constraints of the joints actually. So let me, before we come to the rigid bodies, let's see what are the joints actually. So you can have either revolute kind of a joint, you can have a prismatic joint, you can have a helical joint, you can have a cylindrical joint, you can have a universal joint, you can have a spherical joint. So you can have a different kind of joint. So let me give you an example. For example, our hand, when we bend at knee, so this is nothing but your revolute joint, because you are able to rotate at one single axis. Similarly, like when you are opening a door or closing a door, this door is rotating around an vertical axis actually. So this vertical axis, by which this door is joined with the wall or something, this is nothing but a revolute pair actually. So revolute joint. Why it is called pair? Because you require, for the joint you require minimum 2 links actually. And only between 2 links you can have a joint, and that's the reason they use a revolute pair. When 2 links slide with each other, like for example here in this case, my pointer is visible to you. So this is a prismatic joint actually, because it's able to slide with each other. Also called, also have a translation motion. You can have a helical joint. So when you have a cylindrical joint like a latch of your home actually. So when you lock your room actually, so your latch has a cylindrical joint. You can have a universal joint, you have a spherical joint. A spherical joint is like our shoulder. Our shoulder is a spherical joint because I'm able to get all the orientation, but obviously there's no translation there actually. So how do we calculate the degree of freedom? Degree of freedom is calculated by this formula called Brogdon's formula actually. I'm not going into the detailed derivation of it actually, but you can look into the certain books how it is derived. So this formula is most of the time valid, but certain situations does fail actually. But for your use case, most of the numbers you know actually, this is valid actually. So you can use this formula as small m multiplied by capital N minus 1 minus j plus summation of fi. Now I will just explain what these are actually. So this this small m is where this mechanism is placed. Are you talking about planar mechanism or are you talking about the spatial mechanism? So planar mechanism is like when you constrain a mechanism to be in the plane actually. So for example, you are writing on a board or like a hands of the clock actually. So hands of the clock will move in a plane. This movement of the minute, second, and hour will move in the plane. So this is called planar configuration actually. But you can also have a spatial configuration. Spatial configuration means it's like a driving a car, a manipulator, a space shuttle, a rocket. So they are in a three-dimensional space basically. So planar mechanism, two-dimensional space, spatial mechanism, three-dimensional space actually. So does anyone know that how many degree freedom is like a planar mechanism has actually? Anyone? Can someone guess the number? Anyone from mechanical engineering, third year, fourth year, or graduate? No one? Okay, just guess it. I'm telling you an example of a planar mechanism like this hands of the watch. Okay, clock. So this minute, second, and hours, this hands are moving actually. How many different they have actually? A planar body, how many different they can have maximum? No. I'm not talking about the range of the variable. This minute, second, they can rotate 360. I'm talking about. Okay, see, I'm especially those who went to the James they must have gone through SCM or SCM. So you see that they define the degree of freedom means how many independent motion you can have actually. So you have a planar body. How many independent motion a planar body can have? Yes, so someone's telling me X, Y, two degree freedom. And with this, you are right. That's why and then you also have a rotation in the plane actually. So you have a 3 degree freedom, X, Y, and theta. So just see this example, like I have a phone, and I am putting this, this is the plane. My body can move X, my body can move Y independently. I can have independent X motion, I can have independent Y motion, and not only I can have independent rotation around G axis. So I have a 3 degree freedom. So every planar mechanism or planar body is going to have a 3 degree freedom. Is it making sense to everyone? Yes, sir. If you don't understand, then we are not understanding what I will talk about actually. So please understand. So any mechanism are going to have a 3 degree freedom actually. So two translations, it can translate in X independently, it can translate in Y independently. I'm not talking about the range mental, I'm not talking about the range. What the value in this variable thing I'm not talking about. Value has to be real value. I'm not talking about the range of the variable. I'm talking about how many independent variables can have actually. Means how many independent motion it can have. It can have an X independent motion, it can have a Y independent motion, it can also have a rotation independent motion actually. So for example, I give you an example like our shoulder have a skeletal joint. The skeletal joint means you have a alpha, beta, gamma, but they are constant. You cannot be 360 actually. Okay, so all the joints are not 360, but you can have it is a real value actually. You can see. So now we have understood about the fluid body. Now can you tell me the spiritual body? A 3D body, three-dimensional. This body is three-dimensional. How many dimensional it can have actually? Come on, you should answer it. This is a simple three question. Class 12. Can you please count that? How this five number is coming? Good guess. Answer is not fully correct, but yes, you are right to some extent. So you have three translations. Translation around X, translation around Y, like mentioned in the plural body, the body is constantly changing. So if you can translate X, you can translate the Y and you go around Z. The body cannot come out of the place. But in a special body, it can translate X, it can translate Y, it can also translate in Z axis. So we have a three translation motion. Now, three translation and you can have a three rotation as well. So rotation around X, which is generally called a rolling motion, rotation around Y, because body can rotate around it, that is called pitch motion, and you can have a rotation around Z axis, which is called yaw motion. So you have a 6-degree freedom actually. So three translation and three rotation. So any spatial body, spatial motion are going to have a 6-degrey freedom actually. So in the interest of time, I will have interacted more and maybe give more example, but I'm running out of time, so I will quickly go back to it. So this small m is called what is the degree of freedom available whether the body is a spatial body or it is a fluid body. The value of small m is going to be 3. In the case of a spatial body, the value of small m is going to be 6 actually. Now what is capital M? As I mentioned that Robert is nothing but the connection of the rigid body actually. So capital M and one of them, if you see that, how the mechanism, can anyone give me the definition of the mechanism actually? How do we generate mechanism for the rigid body? See, class has to be interactive, otherwise you will skip, I will just keep speaking something.
अनम्यूट कर यार and mechanism that can form
so actually so I think the connection of the linkages can be the mechanism when grounding is so the grounding of one link how to generate the reaction process to transfer the motion. So for the transfer of the motion, the one of the links has to be grounded and then it starts with the mechanism. So similarly here, if you see here, when I'm talking about the capital N, the number of the links, we also count one of the grounded links actually. With respect to which the later on the reaction forces will be generated and they will be transferred actually. So the ground link also has been calculated. This is true in the case of manipulators actually, because in the case of manipulator, like for example, you see my hand, this arm is grounded to my body actually. So my body is the reason, and then my arm has a certain level of freedom. So similarly, this ground link also has to be calculated. So when I am counting the number of links, I am also counting one layer link which is called ground, and then n minus 1. And one is number and then minus j. J is number of joints actually. So suppose that you have a these many link and these many joints. I must count how many joints the body has actually. And then I apply this formula. M into F minus 1 minus J plus SI. And this I 1 from 1 to 0 means each joint has a certain degree of freedom. As I mentioned that you have a loose pair, you have a prismatic pair, you have a helical pair, you have a cylindrical pair, you have a universal joint, you have a spherical joint. Each joint has a different degree of freedom. Like you can see, degree of freedom of reduced pair is 1, prismatic joint is 1, cylindrical is 2, universal is 2, and spherical joint is 3 degree freedom actually. So you have to sum up all the degree of freedom of each joint. And you use this formula. This is called a Douglas formula to get a complete degree of freedom, because you cannot use the basic way of calculating the degree of freedom using the rigid bodies to a complex mechanism actually. So for this purpose, the Douglas formula has been given and is valid for most of the time. So let me give you an example how the revolute joint works actually. So you can see the revolute joint has 1 degree freedom. Why? Because as I mentioned that any rigid body has a 6 degree freedom. But now this connection of the body, like there was one link and there was another link, and they are joined at this joint actually. And because of this, they have only 1 degree freedom. So can someone tell me what happened to the rest actually? Because I was supposed to have a 6 degree freedom. And I have a 2 rigid body, then I should get a 12 degree freedom. But actually I am getting only 1 degree freedom. Why it is happening? Can anyone tell? Yes?
मुझे नहीं पता ये बोल कर रहे हैं
See, this is the one thing. When I teach, I ask a lot.
क्या
I don't know what कैसे Yes, please. I think I know. Abdul answer. Can you try? What happened? I was supposed to have a rigid body 6 degree freedom. And then I have a 2 rigid body, I have a 12 degree freedom. What happened? I am getting only 1. Okay, so in the interest of time, there is something I should remember in the previous definition I talked about constraints actually. So let me talk about the constraint here. Constraint means you constrain the motion, you do not allow the free motion. So when I put this together, you join, it puts 5 degree constraint actually. What is those 5 degree constraint? See, if there was a complete rigid body, these 2 links were rigidly connected. Like if I do a welding here, so it means no joint, I am rigidly connecting. So when I am rigidly connecting, what will happen actually? There is no relative motion between them. So total degree freedom will be 0. Okay? If there is no like a degree freedom means it can have a no relative motion. But if there was no joint or no constraint, these 2 links, they will not be transferring motion to each other actually. I must put some constraint so that motion transfer can happen. So how many constraints I am putting? Because of this joint, I am stopping the X motion. Because of this joint, I am stopping the Y motion. I am stopping the Y motion. I am stopping the Z motion. I am stopping all the 3 motion actually. X, Y, Z translation has been stopped because of this revolute joint. Not only this, I am also stopping the X motion, I am also stopping the Y rotation around X, rotation around Y. I am only allowing the rotation around Z axis actually. So this is the Z axis, I am allowing only rotation around it actually. So I have a 5 constraint, and because a rigid body can have a 6 degree freedom, because of this 5 constraint, I am getting only 1 degree freedom actually. And one of them I am assuming is a grounded. So suppose that if I assume this link is grounded, this link is moving with respect to this link actually. So this link is moving with respect to a grounded link because of this revolute joint, and I have only 1 degree freedom actually. Why? Because there is a 5 constraint. Similarly, in the case of a prismatic joint, it can only translate. So it cannot move in X, it cannot move in Y, it can only move in Z. But it cannot rotate around G, it cannot rotate around X, it cannot rotate around Y. So I'm giving like a 3 rotation and 2 translation, only around 1 translation. Here, in the case of prismatic joint. In the case of rotational joint, I am giving 2 rotation and giving 3 translation, actually, only around 1 rotation. So that is called a revolute joint. Can someone tell me how much degree freedom this joint has actually. So I can see that it is translating outside and also rotating. So now we look at the helper joint has. So yes, in actually it's like
मैं अनम्यूट कर रहा हूँ
that's what
सब हाथ के पास आए तो
it's
कोई इशू नहीं है नहीं
because helper joint is nothing to do with spin motion basically.
लैपटॉप को देखो
So your net is both motion. No motion is spin or translation motion. All the translation motion is you can see you cannot independently rotate with respect to your translation. This is helper joint actually. It has only actually 1 degree freedom. Basically your theta and L have a relationship. That is there always having a relationship between pitch and rotation actually. So they have a relationship. You are moving L, you must be rotating theta because there is a relationship here actually. They are not independent variables. As I mentioned, degree of freedom means you have to have a real value and also you have to have a independent motion actually. If they are not independent motion, then you cannot always do it. Now, can you tell me a symmetrical joint? How many components it can have actually? Yes. Because if you try to learn on your hospital actually, your latch can rotate independently and translate independently. So symmetrical joint, your latch, when you close it to, has like a 2 degree freedom. No, universal joint, you can clearly see that universal joint can have only 2 degree freedom because rotation around this axis and rotation around this axis. So they are allowing only 2 rotations. They are killing 3 transition and 1 rotation. So that's your universal joint actually. And universal joints are found in many mechanical, if you go to a mechanical workshop, you will find it actually. And there are many systems in your car or manufacturers in car markets, you find many universal joints. The spherical joint has a 3 degree freedom. Why? Because it stops all translation but allows all the rotation. Rotation around X, rotation around Y, and rotation around Z. And please mind here, all the rotation alpha, beta, gamma around X, Y, Z actually they are not 360 degree actually. They are real value within a range actually. So that is the condition required. So that's how to calculate the degree of freedom. Now, Bruno's formula in a broad way, and it will look like degree of freedom equals to m into n minus 1 minus j plus summation of f I number of joints. Each joint has a degree freedom. So if you see here this coin, I'll give you an example of here also. So suppose that this is a coin, like it is supported from US, where Abraham Lincoln is there on the front, and on the back side the number is written. So this coin in a plane, as I mentioned that, is going to have only 3 degree freedom. So you can have an XY to locate the center or any given point into the bit, and also the rotation of the coin actually, at which angle Abraham Lincoln is seen. So it has only 3 degree freedom. But if I take the same coin as a rigid body in a spatial dimension, it is going to have a 6 degree freedom actually. So Goodwin's formula is valid both for open chain mechanism and closed chain mechanism. So what is the open chain mechanism? Open chain mechanism means where the links are connected and the final link is open. This is not closing the loop actually. So that is the open chain mechanism. Like our hand. Our hand is the open chain mechanism actually. And also all the links are serially connected. Means they are connected in a serial manner. One after another, the links are connected. So that's the open chain mechanism actually. And Goodwin formula is valid. This is also valid for closed chain mechanism. Closed chain mechanism means when you stand on the ground with both of your legs touching the ground. So what happens? From your lower part of the body, a loop is going from one leg to another leg and then coming to the ground. You are closing the loop. So this is called closed chain mechanism or closed loop mechanism actually. Where a person is standing with both the feet in the ground, the example of closed chain mechanism. So there is an open chain mechanism, there is a closed chain mechanism. And most common example of open chain mechanism is serial manipulator. Most of the time you will find in a manufacturing industry, the serially connected link, like for example, here I give you example. This is the open chain mechanism because link is starting from here, the ground link is here. All the links are serially connected and the last link is left open. This is called open chain mechanism. But if I connect another link from the last link and close to the ground or close to the here actually, this is a closed chain mechanism. Like I'm sure you must have seen 4-bar mechanism actually. They are closed chain mechanism because loop is getting closed actually. So links or mechanisms that can be open chain or closed chain, and goodness formula is valid for both of them. So let me derive goodness formula from degree of freedom of a 4-bar mechanism. So you can see here. How do I calculate degree of freedom? First, I have to know that small n, and that I will know that either the planar mechanism or the spatial mechanism. In this case, as I mentioned, is a planar mechanism. So small n is going to be 3. What is a capital N? I have to count number of the links. So this is the one link, link number 1, link number 2, link number 3, and the ground is also counted as a link. So I have a 4 link actually. So capital N is going to be 4. So 3 into 4 minus 1 minus j. How many joins I have actually? I will count. Joint number 1, joint number 2, joint number 3, joint number 4. So I have a 4 joint and I have a 4 link. So you can have a 4 minus 4 is 0 and then 3 into minus 1 minus 3. Plus, how much degree freedom each joint have actually? So the first joint has a 1 degree freedom, second joint has a 1 degree freedom, third joint has a 1 degree freedom, fourth joint is having a 1 degree freedom actually. So I will count them 1 plus 1 plus 2 plus 3 plus 4 actually. And when I solve it, so this is called 4-bar linkage slider crank mechanism. When I solve it, I get a total degree of freedom 2 into 4 minus 1 minus 4. This will get cancelled actually. So you will get minus 3 plus 4, which is total degree of freedom. Then equals to 1. So I have a total 1 degree freedom. Now I have listed another mechanism here. Can you please tell me what is the degree of freedom of this robot actually, or this mechanism? Any answer from the audience? In the interest of time actually, this mechanism is also 1 actually by the way. So how it is coming? Let me first count what is the small n. The small n is because this mechanism is a planar bond actually, so it's going to be 3. What is the total number of link? So the first link, second link, and this is also a block. It's a third link. And then this is ground, this is ground, and this is ground. So it is very much like an electrical circuit. They all are same ground. So I can have a 1 ground link. So total number of links are 4. 1, 2, 3. This small block of cube actually. Because this small block of cube is a link. Why? Because this block is rotating within the previous link and sliding within the next link actually. So this block is also a link actually. So 1, 2, 3. And this ground link, please do not take them separately. This link is not a separate link. This is ground link basically. Because this is grounded at both the ends. And this is also grounded. So they all combine together 1 ground link. So you have a 1 ground link and 3 moving links. So you have a total 4 links. So N is 4. And then you apply the same formula because each has a 1 degree freedom. So 1 rotational joint, 1 rotational joint, 1 degree freedom, 1 degree freedom. And then third is also a rotational joint, a W joint, 3 degree freedom. And the fourth is a translational or prismatic joint actually. So you have a 4 degree freedom here. So you just combine it and you get the same formula and the degree of freedom is 1 actually. So the Gruber's formula is valid for most of the situations. You see any robot, you just try to count the number of the links, try to see that what kind of joint they have, assign them, use this formula, you will get the degree of freedom. freedom actually. In fact, you can extend the rigorous formula to very, very complex mechanism actually. Even this is an example of a steamer platform. Steamer platform is nothing but a closed chain mechanism actually. So you can see that there is an upper platform, there is a lower platform, and this lower platform and upper platform they are connected by 6 links. Okay, so these 6 links they are allowing this motion, and this is called a steamer platform. Generally, is called also as a parallel manipulator compared to the contrast to the previous, that is called serial manipulator. And the parallel manipulator are extremely complex actually. The kinematic is extremely complex. But anyway, we are not going to deal with it, but they are very, very important, especially when you have a flight simulator actually. So when aircraft fighter pilot, when they go for a pilot training actually, or even a normal passenger pilot actually, when they go for a training, they do not fly aircraft directly. They try this kind of a manipulator where they sit. The chair is putting on this manipulator, and this you allows you 6-degree freedom, so that you know your yaw, pitch, roll, and all those. You can experience the real, means virtual flying basically. So virtual training of the pilot happen on this kind of manipulator. When you go on any amusement park, there also this kind of maniplators are there, and you can experience the virtual reality. This manipulator also used for a precision manufacturing actually. So where the precision manufacturings are there, this kind of a manipulators are used actually. So it's extremely useful. It's also called as a steamer platform. You have a various communication and common this kind of a platform. And again, you get a very similar formula and you get a degree of freedom 6. So you can see platform, the upper platform has this robot has a 6-degree freedom. Means it can have a 3 translation, it can have a 3 rotation, and you have a total 6-degree freedom actually. Anyway, I'm not going to too much of a detail because this is complex, because I want to come back to the kinematics part. Please give me 5-10 minutes extra because I want to cover that part. So, how do we define the robotic space actually? So we have to have a 3 space. First is called configuration space, and I told you the degree of how to calculate the degree of freedom of the configuration space. And then after the configuration space, I will mention that configuration space also called a C space, and it's an abstract space actually for use for mathematical modeling of the robot actually. So what is the work space? Workspace is a space where end effector of the robot can reach actually. So it's like my hand. My hand can move, like for example, I don't know, the camera is visible or not, so you can see like my hand is able to move in this space. So my body can have a very high degree of freedom, like my body has around 30 degree freedom by the way, people know it. But my hand can move in the space, and wherever my end effector of my fingers can reach, because I can only manipulate my finger. So where my end effector can reach, and how many degree freedom my end effector can have, that is called workspace actually. And after the workspace, there is something called task space actually. Because your workspace can be different from your task space. So this is like, I'm a human, and I'm asked to write on the board actually. And board is a planar system. Like for example, I'm writing something on my wall actually. Wall is a planar wall actually. So my task space configuration, task space degree of freedom depends what is the nature of the task. So if I'm writing on the board, I have only 2 degree freedom actually. But suppose that I'm able to rotate as well, I have 3 degree freedom. But in the plane, I can only 2 degree freedom. I'll just give an example. But if I'm pulling a bottle and I'm drinking like this, so I have 6 degree freedom because I can pull the bottle, I can move X, Y, Z motion, and I can rotate, I can pitch motion, I can yaw motion. So my task space can also have a 6 degree freedom actually. So task space depend on your task actually. The task that is given to you, work space depend on where your end effector can move and how many degree freedom end effector can have. Configuration space is where your robot lies, complete robot lying in the configuration space, and each point in the configuration space defines the configuration of of the robot. So it is actually 4 o'clock. How much time I have? Can I go into the extra for a minute?
Yeah, yes, yes, sir. Yes, sir, yes, sir, please continue.
Yeah. So, Dr. Rajesh, I will just take a 5-10 minute extra so that I give you some overview actually. So, what happens when you have a rigid body motion? So, I have a already like a configuration space, workspace, task space, degree of freedom, already calculated actually, and then you go for a rigid body motion. How do we represent the motion? So I will not go in of the mathematics part basically, detailed mathematics, but I will give you an overview idea. So what will happen when you want to define the motion of a body? What do? You require two frames. The first frame is called a fixed frame, which is in a space or in the environment actually, which is represented by a totally basis in S. We call it a space frame or fixed frame. And then I have another frame which we represent by curving basis of B, which is called the body frame. And this body frame is embedded in the body actually. So this is body moving. So once I have this two frames, one frame or space frame, or we call it S frame, and I have a B frame or call it body frame, then what will happen? I will fix this body frame with the body, and I have a fixed frame S actually, and then I forget about the body. For example, let me go back to the previous example which I gave you here. If you see here, so what I will do, I will put a frame here, like I'm putting a one frame here, this is the fixed frame, and I will put a frame here actually. So this is a body frame. And once I body frame actually, I will forget about the nature of the body. I just only bring the frame actually. So the motion of this frame, with respect to the motion of the space frame, I will be able to define the configuration. Because if this frame is rotating with this frame, I know that this link is rotating with this link actually. If this frame, similarly put the frame here also. So when this frame is translating with respect to this frame, I know that this body is translating with respect to this body. Means you forget about how the shape, size of the body looks like. You fix the frame and then you plan the motion of that frame actually. And when you plan the motion of this frame, you are able to write the kinematics of the body actually. So that is what we will be doing in this section actually. I'm sorry, I don't have much time, so I cannot go in detail how we write it, but I will just give you very high level overview here. So I have a rigid body. In that rigid body, I will fix a frame, and then this frame is moving and rotating with respect to this frame. As I mentioned that when there are two frames, they can rotate with respect to each other and they can translate with respect to each other. So there can be three translations and there can be three rotations. So translation around, for example, I will say that this body is rotating. Okay, let me get the laser pointer. Okay, so this body is rotating and is translating around the x-axis, y-axis and g-axis. And then is also rotating around axis, y-axis and g-axis. So I have a singularity here. So it means tracking the motion of this frame, x, v, y, v, z, v, with respect to axis, y-axis and g-axis, I will be able to write a kinematic equation actually. And that's how I have a multiple link. At each link I will put a frame and then I will plan the motion of each frame with respect to the previous frame or with respect to the ground frame. I will be able to write the kinematics actually. So what these frames, they form something called a spatial orthogonal group. And when I have this frame, so I have two entities, translation motion and rotation actually. So rotations are governed by a rotational matrix called R, which are written in 3 cross 3, which are orthogonal matrix. There is spatial orthogonal matrix. Orthogonal matrix, why? Because these frames are orthogonal to each other, these axes are orthogonal to each other. So axis, x-axis, y-axis and g-axis, they are orthogonal to each other. They are orthogonal matrices actually. And spatial, why? Because their determinant is 1 actually, and we use right-hand coordinate system. I'm sure when you use Lenz law and screw rule, when you use electromagnetic or mechanism actually, so we use right-hand rule. That's correct. So we call them spatial orthogonal. Although this is a part of abstract algebra, which we what are the rotation of a frame, body frame, with which the body frame can be related by a rotation axis R. And this rotation axis R are going to have a 3-column vector. So these 3-column vectors are nothing but the basis vector of those frames actually. So what will happen? I will just quickly show it here. So suppose that this is my body frame, this is my world frame, and I want to estimate the rotation and translation of the body frame with respect to the world frame, and I will be writing this kind of a rotation matrix. So you can see this is XB, YB, and GB, and then unit vector. So these are the basis vector of body frame. This basis vector of body frame we are written in a world frame actually, like this. So this is a body frame XB, vector of this basis of a body frame YB, the basis vector GB. They are written in a world frame, XS, YS, and GS. And these coordinates are they are put as a column vector. And this creates the rotation matrix. Means, like for example, this slide I will show you. So here, so you can see, suppose that these are the frame. Okay, but how I will show this. Okay, let me just have a pen. Okay, so suppose that you have this. You have x-axis, you have the y-axis and g-axis now. So when this is your space frame, and then suppose that this is your. So this is your body frame actually, yeah, body frame. So when you are aligning, then translated and rotated actually. So you can see, you can initial alignment. So XB is along with the axis, YP is along YS, and GB is along GS actually. And when this body and the rotate, you can then translate the body. So now what will happen? This frame is rotated and translated within the frame actually. So when I plan this motion of a rotation and translation, I am able to write the configuration of the body frame using the world frame. And that's how we write the kinematics of the body. You understand the point? So what you do, you have to get the basis vector of the body frame, you have to get the basis vector of the world frame or space frame, and we have to write them in the each other's relationship actually. And that relationship is governed by this matrix actually, rotation matrix R actually, looking at the rotation, and then translation. Translation means the origin of the origin of the body frame, how much it is translated to the origin of the space frame actually. So we write this translation vector. So this rotation and translation together they represent the configuration of the body frame actually. So I will just first form. Okay, let me come to the kinematics part quickly. So what will happen? What you do when you write the global kinematics, you put a frame at each joint. So base frame, the next joint, at each joint you put a frame, and then your end effector frame. So kinematics means I want to know what is the orientation and position of end effector frame with respect to the base frame. That is called forward kinematics. You understand my point? Everyone does understand this? I want to know the position and the orientation of the end effector frame with respect to the base frame. Although you can have many intermediary frame as well. So when I use this intermediary frame and then I calculate what is the orientation and translation of end effector frame with respect to the body of base frame, I am able to write the forward kinematics actually. So forward kinematics means I have a joint space like a theta 1, theta 2, theta 3 or Q1, Q2, Q3. From joint space I am able to calculate the orientation and translation of the end effector frame. That is called forward kinematics. And forward kinematics is always unique in the serial manipulator actually. And what is the inverse kinematics means? If I tell you where is the end effector, can you tell me what is my joint inverse? What is my Q1, Q2, Q3 and all those? That is called inverse kinematics. It means if I give you x, y, z and omega gamma, can you please calculate what is my joint inverse? That is called inverse kinematics. And unfortunately, inverse kinematics have a multiple solutions. I can give you an example here. For example, this end effector is here, but it has a two configuration. It can have a base upper hand configuration or lower hand configuration. So inverse kinematics can have a multiple solution, but forward kinematics is always going to have a unique solution. If I give you theta 1 and theta 2, the position of xy is fixed. But if I give you X and Y change instead of n effectors, theta 1 and theta 2, they are not unique because they are able to get a form like a second order equation actually, polynomial equation, and this polynomial equation has quadratic equation has a two solution actually. So you have upper hand condition, lower hand condition. So this is called forward kinematics and inverse kinematics. Is it making sense to everyone?
Yes, sir. Yes, sir.
Any question here?
I think we are just running short of time, so let's go ahead. So, you think that this robot kinematics and dynamics extends through various courses, and in this short one lecture, it is nearly possible.
Yes.
But I hope that students might have got a good sensitization what this introduction about the robotics and about kinematics and dynamics of robotics. I believe is very important when you are going to design robotic systems. So thank you very much, sir. I think next Dr. Adisham has already joined. So thank you, sir, for this insightful lecture. I hope that students have got sensitized about that. So we all thank you for that. Thank you, sir. Thank you very much.
Thank you very much. Thank you for giving the opportunity to present my work. Thank you.
Thank you, sir. Hello.
Yes, sir.
It didn't make it, so but still, it's good to see you online also.
Yeah. Actually, there was some unavoidable reasons and some other commitments, so we could not come there. But we will try our level best next and sometime in coming days or near future. We will, try to come there. Yeah. Yes.
Okay, thank you, sir. So, participants, we have with us Dr. Anish Shah. He's an assistant professor in Center for Artificial Intelligence and Robotics. His research interests include digital servo, robot learning, autonomous navigation. Dr. Shah is PhD in electrical engineering from IIT Kanpur, and he has been associated with IIT quite long time. So today he will be delivering a lecture about robot programming with robot operating system and visual servoing and robot learning. So it's over to you, sir, because we are already late. It's 4:30, so we are having maybe 10 minutes with us.
Yeah, sure. So, thank you very much for kind introduction. Here I would like to ask audience, they want to take a break for few minutes or we should go ahead. How it is? Yeah, please ask audience, so there should not be disturbance when we start. So during a session, we want again audience will focus on the topic.
Yeah, maybe continue, sir, because by 5 they are going to leave. They have a bus to catch. So
Okay. Yeah. Right. So yes, I'm going to share my slides. First, let me share from my. Please let me know if it is visible to you all.
Yes, sir.
yeah, so it is visible. It's building right now, but it's visible.
However, could you please let me in? I am trying from other window as well, so I can see the presentation. When I am talking to you. So yes, it is coming from my some account, I believe. Hello, can you hear me?
Yes, yes, yes.
Okay, please give me feedback and whenever I ask, please give your input, which are valuable. I should know that everyone is on the same page. Right? It is required. Dr. Khan, please, I need your input as well.
Yeah, okay.
Yeah, so that is possible. See, here I am going to share from, screen from my end. Once it is okay, please let me know.
That is visible.
Okay. Audience, are you all with me?
Yes, sir.
Okay. Good afternoon to you all. So, are you ready to learn something about the robot programming,
Yes, sir.
especially in India?
Yes, sir. Yes, sir.
I'm waiting for your input. See, I can tell you what I will do. I will introduce some basic concepts and the purpose, objectives, and I will showcase some of the applications. And after that, I will show you some of the demonstrations, recorded video, as well as with the help of real Can you see that? Setup. This means there are some sensors, and actuators. Hello? Is still this?
Yes, it seems to be okay now.
See here, at the end, if time permits, I will showcase some of the real-time demonstrations that give you the feeling about the importance of the remote programming and how you can handle the real hardware, including different sensors and actuators. Is that fine? But again, it is conditional if time permits and your interest lies. Okay? So I start. Here, robot programming because see here, first question you should ask yourself to do programming. Any audience who can answer this question?
Because without instruction
Question is displaying in my slide as well. Audience can take a moment to think about an answer. Why we need? See, without purpose, without setting our goals, where we can land up, no one knows. No one can help us. Right? So first we understand the purpose, why we need. Take a moment and answer. Please do not hesitate. Okay. If you want to take some time, I should wait for the input. Yeah. What else? Yes.
What is why robot operating system? Because without instruction it's useless. Okay. Navid bolo. Am I audible, sir?
Okay, only one input.
Sir, because without instruction a robot is useless.
Okay, your answer is lying here. That is the answer, right? Now look at the next question. One more question for you. Why do we prefer it? Because what is the reason?
So they are saying that when am I audible, sir? They are saying that when you have a dedicated operating system to operate the robots, it becomes easy to connect different devices together on a one platform. Otherwise, it will be difficult to interact with the different devices.
Okay. Yes. I could not hear you properly.
So they are saying, if,
Hello?
yes,
Your voice is not clear. I don't know what is happening.
is it clear now?
Yeah, it is better. Yes.
Yeah.
Please go ahead.
Sir, it is important. We prefer robot operating system because it gives us a unified platform for devices to connect and communicate with each other.
Now I am going to showcase one demo here, the live demo. Okay? For that, I will turn on the video. Could you see now this hardware?
Yes. Yes, sir. Yes, sir.
Can you see that? It
Yes,
is
sir.
robot manipulator. Okay? I need input from the audience.
Yes,
Otherwise,
sir.
there is no need to put such efforts to make you visualize what we are doing here.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. We can see it.
Yes, thank you very much for your input. Now look at the screen. Okay?
Yes, sir.
Can you see the SAM? Can you visualize the SAM robots here in a digital domain?
Yes, sir. Kind of, sir. Yes.
On the screen which is in front of you. Give me input, please.
Yes, sir. Yes, sir.
Very good. Now could you please change the position? Yeah, very good. Yeah, hold on. So look at here the cursor position. Okay? At the same time, you can also observe the real hardware. Now I am putting in a such a way that you can see the screen as well as the hardware at the same time.
Sir, can you please put that screen share off so that we can completely share? Yeah, please.
Sorry, what is your
स्क्रीन शेयर जो आपने कहा किया ना उसको थोड़ा बंद कर दीजिए so that we can see this fully.
I cannot hear you.
It's okay now, it's okay.
Hello? Dr. Sir, I cannot hear you.
So actually they are coming from different areas. So actually I was waiting for their answer. That's the reason.
Yeah, so, yes, hello?
Yes, sir.
So you can mute the other screen and the person who is speaking, please unmute and speak. So the echo sound should not come. Yes, yes,
Side
it is
loudspeaker
better.
off.
There are 2 minutes only to answer one at a time. आप आगे जब पेशेंट का पे स्टूडेंट है
See, I think there is some issue from your end. Somehow I cannot understand what you are speaking there. I think Dr. Afan, something else is coming. The actual voice is not coming to me. Uh, there's some glitches at your end, it seems, I believe.
I guess that this is okay now. Actually, your screen was not completely visible. The demonstration that you were showing. So, but I believe that it is visible now. Just one minute.
सर एक्स कैप्टर हो गया क्या वो होता है
Login limit हो गई.
हॉटस्पॉट ही दे दो कोई फोन का इसको और फिर हॉटस्पॉट नहीं चल रहा है नहीं चल रहा है क्या
It may be. the multiple robotic systems. Slides I can see. This is appearing soon with such network tools. So there are some region for ROS, right? See here, one reason is it has sorry, in between I got the call, so I declined. So there are tons of tools. It supports high-end sensors, actuators, communications between different devices, modularities, and inter-platform operabilities. These are some of the reasons. Okay? Here with me, there are some demonstrations. Please look at, but that slide is not coming. Are you able to see this video? Yes, sir. Yes? Yes, sir. Okay. Are you on? Are you on with me? Yes, sir. Okay. Look at this video. And please do observe. And at the end, I may ask you what you have noticed. Third video. Fourth one. Are you able to see, right? Sir, yes or no?
Actually, sir, the video
Is it not? Is it not visible?
Yeah, it is little bit. That robot harvesting.
Sir, it is visual, but the video is not playing smoothly.
Okay, okay. Because of lag, but you are you able to observe the task what robot is doing?
Yes, sir.
Okay, very good. Okay. Hold on. Meanwhile, I will show you one more demonstration lifetime, and please hold these observations for a moment. I will ask you soon about this. Now you look at there's one more device in my hand. Can you see that? Can you see it? Please look at another window from where I logged in.
I guess video is off, sir, in that
Are
another.
you able to see it?
No, video is off.
Sir.
There is a device is in my hand. Okay? Yeah. This is pixel controller. Flight controller that we generally put. No, that is fine. But I am actually talking about the another window. Here you see
आराम से ना पीछे से नीचे शिफ्ट करो, ठीक है? लेकिन आराम से बैठना होगा।
उस वाले साइड से बैठो पहले।
जो
माइक ऑफ कर वो नीचे से रख के आवाज वाले साइड से बैठो आराम से।
in that video.
Here the rods. And if I show you, you can see here, these are the topics.
cannot think of without programming. With the help of sensors, actuators, computing device, and the programming, you can only think to make it autonomous. So this is essential component. In fact, in general, if I talk, you need perception, you need planning, you need control to achieve autonomy for any robotic system. Now look at human robot interaction. Look at the artificial intelligence. Have you all aware about the functions of natural instinct? Right? How it works? What are the functions that it does? Right? Can you imagine to create artificial instinct that mimics the behavior of natural instinct or human instinct? You have seen, I have shown you a couple of demonstrations, real-time demonstration of robotic systems, right? But can you imagine to create the artificial instinct and attach to it? So the moment robot is going to touch the apple, the fruit-looking example that you have seen, the robot was trying to identify the apple of fruit and grab that apple and put it somewhere into the basket, right? However, if you notice, the robot is capable of some kind of perception where it is going to touch the object of interest. That is the question. Now here, the next demo I am going to tell you, I am going to show you, that is related to artificial and along with the programming. The programming can help you to perceive what the artificial skin is going to. Look at when we touch that screen, then I'm going to touch that artificial skin. And at the same time, I will show you there is a deferment in the system to perceive the of touch. Here it is. Look at it. Look at it. This is the device, right? Can you see that? Yeah, this is the device and this is the skin of interest. Okay, I'm touching it, right? And this is the real-time feedback. If you know the programming, you can show the difference. You can showcase the difference, how it works. Can you see? And there is the interfacing. This device here, there is a connection with the system. Can you see the connection here? This is the cable that is attached to this laptop.
Yes, sir.
And in front of a screen you can see. Now at the same moment, right? If I touch this, you can see the difference there in the signal. Can you see that?
Yes, sir.
This is another example to give you the feel how important the programming is. Try to understand. So in short, whether you have artificial intelligence, whether you have
Yes, sir.
Yes or no?
Yes, sir.
Are you all interested? Should I take you now to give you some concepts, some examples, some insights, how you can achieve such autonomy?
Yes, sir.
Okay, so let me resume my presentation again. Hope you are all with me and you all get it, right?
Yes, sir.
Yes, sir.
Okay. Thank you very much for your interest and time. Yeah, there's some delay here. I'm trying on my another. Yeah, now it is in sync, right? Okay. We have seen the examples, and we understood the role. Okay. The next level is, you know, here I will come back to this slide after context. Okay. See, what it is, is is a set of software, libraries, and tools. Right? I'm talking about the robot operating system. Hope, are you all with me?
Yes, sir. Yes, sir.
Please give your input.
Yes, sir.
Okay. And there are some prerequisites. You need Ubuntu, you need specific distribution of ROS, and you need at least one programming language knowledge, Python or C++. If you know both, it is good. And there are some specific versions aligned with the specific version of Ubuntu. Right? Here you see that. So, for example, if you have installed 20.04 in your system, you need to install newest version of the ROM. Everything is fine till now? So far so good? Should I move ahead? Okay. So now look at the general concept. What is general concept is? So how it works? This is under autonomous first. And after that, you can run this many nodes. For example, you have right, for example, node 1 is for camera 1, node 2 may be the sonar node, node 3 may be the robot gripper node. Okay, and so on. However, when you try some machine, for example, quad rotor, it is actually operating maybe a couple of meters away from you, right? Yes or no? In case of quad rotor, it is not observant with you, right? And if you attach sensors, actuators, or onboard computers over there, they are also at some distance from you, right?
Yes, sir.
Because they are on board. So, if you want to visualize what your quadroter is looking at, what you will see, right? So there are, here you see, either in single system or in multiple systems case, you have multiple nodes, right? Yes or no?
Yes,
Question is for audience.
Yes, sir.
Are you able to visualize? Right? There are multiple nodes. So now, how they can communicate with each other? Correct? So there are some different methods. Right? I will show you. I will skip this because we are running out of time. If somebody is interested, I will take him or her in depth. Okay? So first, communication method is topic. You see here,
Yes, sir.
Did you observe that? Yeah. So what is happening basically? Here one node is acting as a publisher. One more node is there. It is acting as a subscriber. Correct?
Okay.
Yes or no?
Yes, sir.
And there is a in between there is a topic. In between there is a topic. Please look at this cursor movement. Okay? And this publisher is keep on publishing some data on the topic, and the subscriber is keep on fetching the data from that topic. Correct? So this is a one way of communication in ROS. Are you all with me?
Yes, sir.
Should I move ahead?
Yes, sir.
So look at one example. Look at one example here. So here we are going to show you that sonar sensor data, we are going to put one of the topics. So you see that with the help of this, I am fast forwarding it just to save our time. There is a chatter topic, right? You can see there is a chatter, name chatter topic, and this is the data which is coming from the real sonar sensor. Okay? Yeah. Next, I am going to look at audience. Are you all with me?
Yes, sir.
Okay. Now, what is the time now? What is the time now?
So we have 10 minutes more. I'm so Ishad. 10 minutes, sir.
10 minutes more. 4 is fine, but I wanted to get the answer from audience. So we indirectly, so it is basically the phone.
Am I audible to you, sir?
Yeah.
Actually, I find very interesting, but I would suggest if we can, if you have a time,
What
maybe.
may happen with the communication?
Sir, can you hear me, sir? Hello.
I'm waiting for your response. Yes, you are audible.
Yeah, actually, what I feel is this session is very important, but they have just 10 minutes now.
Yeah, I can hear you. Please go ahead.
Yeah, am I audible, sir, now? Hello. Hello.
Yes, you are audible, but sometimes your voice is breaking.
Now, what I'm saying, sir, they have just 10 minutes left now because they have to just catch the bus. But what I feel that this session is very important. It was practical oriented, so they are very much interested. Can we continue this session some other day also, if you have a time?
Give you an audience. I don't mind.
Yes, sir, we'll definitely we'll do one thing. We'll give you one more date when if you will be free, and then we'll continue again with the same lecture.
Yes. So I will do once. I will try to wind it up. Okay.
Okay, okay.
So make your audience free. Okay. Okay. Fine. So I will give you the other kind of learning example. Now we have seen the classic way of programming the robots, right? Now look at this screen. There is another way of Next question. Can machine or the robots human action? Right? So this we call robot programming by democracy. The way we teach the child how the A alphabet should be written, right? How he should learn to perform some mathematical or arithmetic operations, right? Similarly, can your robot learn something? Look at the figure A. In a graph, there is some trajectory from start to goal. Can you see that?
Yes, sir.
Yes, sir.
Okay, so my question is, can you teach your robot to learn this trajectory? So the next time it will actually go autonomously from the start to the goal point. That is the question. And here I will show you one example, robot learning demonstration, where we taught the robot to learn this particular part. And look at this window. This window, it will track the trajectory. Second window, the initial point is different. Third, there is a change in the goal point, and in fourth, there is one obstacle. If you observe all four videos carefully, there is a deferment in each task, right? So your robot that you taught is able to, now your learned robot is able to handle the real world situation. Look at when you have multiple obstacles in front of the robot. Still your robot should be able to avoid these obstacles, and while following the path to reach the goal, even the modified goal. So there is a work teaching you, because after learning the robot should be able to generalize its learning. And here these are the examples where you learn robot defining the specific path or interpolation, or there may be some static or dynamic obstacles in the path section, right? This is the example of robot learning by demonstration. Because of time constraint, stop here, and we may about Dr. Khan, is it fine?
Yeah. Actually, your voice was breaking sometimes, so we are not.
I don't know.
Last part we are not able to listen properly. But anyways, I believe that it was very interesting lecture. But this should continue because there was some lagging also. I wish if it would have been offline, it could have been very nice. But with your permission, sir, if you have a time, we'll arrange one more lecture for the students particularly, so that they can get brief more sort of sensitization